For the next hour, I'm going to start talking about burning solids. And burning large solids really is a big distinguishing characteristic of fire researchers compared to most combustion researchers. So I'm going to talk about two standard tests that burn solids. And there are a few ways in which solids are even more difficult to control and to burn than liquids. And in one way is that these large solids, as they heat up and burn, their character changes. If you take a pool of gasoline and you ignite it, it continues to be gasoline as it burns. When it's half gone, you're still burning gasoline. When it's all gone, the last molecule that leaves is a gasoline molecule. When you burn wood, initially you heat it up, and what comes off? Hydrogen. Initially you're burning hydrogen, you get a blue flame. Then shortly after you start liberating a little carbon monoxide, and you also get a blue flame. And then later maybe the methane comes out, and then the ethylene, and the bigger molecules, propane, and you start having larger molecules, carbon molecules coming out. And so the flame continuously changes. It changes from blue to now become yellow. And so wood and almost all solids, they're not a monomer. So as they burn, the species that they're liberating, that are gasifying, change, usually become heavier. And not only that, but at least for wood, you form a char layer on the surface, as I talked about with the smoldering experiments yesterday. And this char layer now is basically solid carbon. You know, it has, carbon has a gasification temperature, I think 4,000 kelvins. So no flame is gonna vaporize solid carbon, but the flame can heat up the carbon and that can conduct down to the virgin fuel and vaporize that. So the charring is very complicated, and now the wood starts to crack. And you have micro bubbles, and you hear, when you burn wood at a campfire or in your fireplace, you hear popping, the little micro bubbles that pop and explode. So burning solids is very much more complicated than gases and liquids. Not only you can't really control the burn rate very easily, but what you're burning changes with time, and the morphology changes with time. And one more complication is that most solids won't just burn on their own. You know, if you hold a blowtorch to this table, you can damage it, but it's not going to start burning on its own. So in order to burn wood or carpet or, you know, any of the furnishings, certainly in this room, you need to apply an external heat source. So if you have a strong enough lamp and you're irradiating this wood with, say, 30, 40 kilowatts per meter squared, now if you hold a torch to the wood, it will ignite and burn on its own. So fire researchers, it's like doing combustion research with two hands tied behind your back. Burning these solids introduces a lot more complications than burning gases. And one way we deal with the complications is to do more repeat tests. If you get enough statistics, eventually you can believe the data. And also to accept a relatively high level of scatter, and to accept also that sometimes in the analysis, it's difficult to do the real high accuracy type of analytical modeling that maybe you see with Moshe Madelon in the mornings here. So with that, I'm going to talk about two different standard tests, both of which burn solids. And I'm giving the same acknowledgments as the last hour. Andre Marshall, Jim Quinteri, and Stas Stoliarov helped me understand this material and prepare the slides. So this is a picture of a cone calorimeter. I love this picture, except that the person should be wearing glasses. We have in our department, PR is a big deal. We try to take a lot of pictures and put them on our website. And every time I see the camera come out, I remind people, put on glasses. We can't put it on the website if it looks like this. So this isn't somebody I know or somebody from our lab, but he is looking at a cone calorimeter test. And it's called a cone because it's a conical heater that captures all the products of combustion. And I'll talk about that a little bit later. But you can see he's burning a solid fuel. And the part that you can't see is that there's a radiant heater, an electrical heater, about the height of his forehead there, that's heating the wood specimen to make sure that it continues to burn. The specimen is always square, 10 by 10 centimeters, so it's a small sample. And the cone calorimeter really is the Cadillac, the most prestigious of the standard fire tests. If you want to characterize how a solid ignites and burns, really the number one test that's performed is the cone calorimeter, whether you're looking at wood, fabric, even lithium-ion batteries, carpet. The cone calorimeter is a great place to start, and you can measure a lot of standard fuel properties with this test. So this is a picture of what a cone calorimeter looks like, a little sketch. And off to the right there, you can see the specimen, again, 10 by 10 centimeters. So you don't need a lot of material. Sometimes for expensive materials, it's really nice to be able to work with a small sample. And that sample, that specimen, is heated by an electrically radiative lamp, basically, heating coils that heat up the sample until it gets basically to its fire point and it can be ignited. Now, it's a conical heater that's hollow, and there's an exhaust fan that's sucking the exhaust out so that you capture all the products of combustion. And not only you capture a lot of products of combustion, but it's open on the bottom, so about 10 times stoichiometric air flows into the cone calorimeter. You're not oxygen starved. And up at the top then, in this hood, as I'll talk about later, is a calorimeter. It measures calories. It basically measures the heat liberated by this sample as it burns. So this is, again, an ASTM standard. It gets updated every few years. It was last updated in 2022. It's a bread and butter. Wikipedia gave a nice quote. It said it's the most significant bench scale instrument in the entire field of fire testing. It's quite popular. We have 2 in our department in College Park, Maryland, but about 300 exist worldwide. And what ultimately it tells you is how do different materials respond to radiative heating, and you can do a test either with or without an igniter. So these are the key measurements that the cone can perform, and there are many of them. First is the ignitability, how easy it is to ignite a solid fuel, kind of like we saw with the Cleveland Open Cup. How easy is it to ignite a liquid? In other words, how much of an external heat source do you need for it to ignite? The second thing we can measure with the calorimeter part of it is the heat release rate. How much, when it burns, how much heat does it burn? How fast does it burn? We can measure the burning rate. We have a load cell under our cone calorimeter, so you're constantly measuring the mass of the specimen. So you take the derivative and you can get the burning rate. The heat of combustion is a tremendous property to be able to measure. Of course, a fuel with a high heat of combustion as it burns liberates more heat and is more hazardous. And then smoke production rate. Most cones do have a laser extinction system on the exhaust to measure how much smoke is produced. We don't use ours that way. We have other ways of characterizing smoke, but it is a fundamental measurement that the cone can do. And all of these are pseudo fuel properties. They really don't depend so much on the test, but they're really a property of the fuel, and they can allow you to rank different fuels and get a quantitative measure of how flammable different solid fuels are. Okay, all cones have a control where you can adjust the external radiative heat flux. Very few solids in that size, 10 by 10 centimeters flat, will just burn on their own. So almost all, and certainly if you had a solid that was that flammable, like a sheet of paper, you really wouldn't want to use that as a construction material. So almost all tests for the cone require that external radiative heating, and it's adjustable usually from, say, 10 kilowatts per meter squared up to 50 or 60 kilowatts per meter squared. Some cones have excellent control over the air that flows into the cone, and you can actually run them with vitiated air. But most of them are like ours, open to the atmosphere. So the applications are, as I mentioned, getting quantitative measures of the flammability of different materials and different products. Even like a lithium-ion battery, it's not a single material, but you can test these in a cone for sure. The results can be very helpful if you're running CFD simulations or zone models. If you're looking at a fire in an enclosure, like a room like this, then knowing the cone material behaviors of the materials in the room can be very helpful for your CFD. It can be used for performance-based design. Basically in fire protection engineering, there are 2 ways of designing occupancies like this one. You can either go by the standards, which is how wide is the door and how high is the sprinkler, how far apart are the sprinkler heads. That's standard-based design, or you can do performance-based, where you actually run a CFD model and show that because this is an unusual shape, that you can protect yourself against a design fire. And the cone also, so it's used not only for fire protection engineering and the design of occupancies, but also for research. So it's not a very old standard. It was developed at NIST, also in Maryland, in the 1980s, and then commercialized in 1986. It really took over the field quite quickly. And what it replaced was far inferior for several reasons, as I'll talk about. But in 1988, it won an R&D 100 award. It's the most prestigious award in the United States for technology. So it really, within a few years of being released, it really demonstrated its worth and has continued to grow and be accepted worldwide. It's now covered by an ASTM standard, an NFPA standard, and an ISO standard. So here again, it's the same person without his glasses looking at the cone. On the left is a slightly better view looking up where you can see the electric heater, the radiant heater that irradiates the fuel. And so it's kind of like an electric stove where you might boil water. And so it's a helix shape, windings of electrical heaters that glow red hot. And of course, you want to calibrate your cone so you know how much heat you're getting from your radiant panel. And it's designed, it's in a position such that the heating of the specimen is pretty much uniform across the entire specimen. So if you dial in 20 kilowatts per meter squared, it should be the same across your whole 10 by 10 centimeter sample. At the right, there's a glass chimney, but we don't use the glass chimney on ours. These are what some modern cones look like. And many of these are computer controlled, and often you just push the start button, kind of like I showed with that closed cup fire point tester before. They cost upward of $80,000, $100,000. They're automated and accurate, but we do have one in our department, and they're hard to maintain. It's not the kind of thing where you can open the panel and check the wiring and replace components yourself. Usually, you need a service contract and someone to come out and take care of it. It's not small, like the Cleveland open cup tester. You can pick it up with your hands. The cup burner that I showed, the chimney is the biggest part, but the whole thing you can pick up with your hands. The cones are large. They're almost the size of two of these tables at the front. Maybe if you took two of these podiums side by side, you'd be getting close to the size of a cone. And then also there's a pretty large flow rate, so you need a good exhaust system to blow the exhaust out. So these are what more modern cones look like. I'm not going to play any of these videos, but if you're interested in them, they'll be in the PDFs, and you could go watch some of these videos. Okay, so back to the heater now. This is sketched on the right. So at the bottom, you have a specimen, 10 by 10 centimeters, and it's usually put on top of a piece of inert fiberglass or KO wool. And then 25 millimeters above that is where you have this conical heater. And those black circles, the solid black circles then, are the electrical coils that get red hot, electrically resistive heating and provide the heat flux that you need to the surface. And then the flow is up and out, the blue arrow. To the left is shown the igniter. In this case, it's not an open flame, but a spark. It's just a spark plug that continuously arcs 13 millimeters above the specimen. Okay, and the heat flux here, I guess some cones can go much higher. We try not to run ours past about 50 or 60 kilowatts per meter squared, because the longer you run it at high temperatures, the better the chance of damaging the coils, but they do go up to 100. Now, the procedure for the cone and the way these cone tests are operated is split into two parts. So the first part is the ignition test, and the second part is the burning test. So the cone ignition test, it's really similar to the fire point tests I showed before. You slowly increase the temperature of your fuel specimen, of your solid. You constantly have an arc spark ignition source, and you record the instant at which it ignites. And then once it ignites, the test is over. You've finished your ignition test. Now you're actually embarking on a burning test. But for the ignition test, what you're interested in is only that instant, that moment of ignition. So in the ignition test, we measure 4 important things, and 3 of these are fuel properties. The first is, after you put your specimen in, how long did it take to ignite? So this is the ignition delay time. It could be 10 seconds, it could be 3 minutes, but that's an important parameter that you measure. The second thing is, if you go to lower and lower heat fluxes, so lower and lower voltage on your electric heater, what is the minimum heat flux for which that fuel will ignite? So, as I mentioned already, with the blowtorch, you can't ignite a piece of wood without external heat flux. But if you apply a heat flux to most wood of about 15 kilowatts per meter squared, that would be approximate minimum heat flux for ignition for typical woods. So this is an important parameter. And of course, if you can find some kind of a wood, lots of times people will put a protective coating on the wood or make it denser to try to increase that number higher. If you can sell a wood that ignites at 30 kilowatts per meter squared instead of 15, then that's a more fire-safe material. The third one is the thermal response parameter. I'll talk about that a little bit later. And the final one is the ignition temperature. What is the temperature of the surface of that solid at which it ignites? Again, so we're going to be able to measure these 5 parameters in the ignition test. So the first one is the minimum heat flux for ignition. So in the plot at the left, what's shown here on the x-axis is the heat flux. So this is the external heat flux coming from that radiant cone. And those on the y-axis is the ignition delay time. How long it takes, is it 30 seconds or 3 minutes? How long does it take to ignite? And as you would expect, when the heat flux is high, it ignites very quickly. And when the heat flux is low, it takes much longer to ignite. So that's where you kind of see this decreasing time with increasing heat flux. And if you go low enough in heat flux, then it will never ignite, at least for most materials. So for most woods, if there's no external heat flux, it will never ignite. Now, the standard tells you do a bunch of these tests and go lower and lower, and then you kind of eyeball it, and the standard says just pick a vertical line, which is your no ignition line, and this is your minimum heat flux for ignition. But of course, to really demonstrate that, it would take infinite time. So you would really need to wait there for hours to be able to demonstrate it. And what I prefer to do is to change this plot, and plot 1 over ignition time versus the heat flux. And now in this case, you can take all your data, fit it with the straight line, which usually you get pretty high regression coefficients. And now the x-intercept is your minimum heat flux for ignition. So it sounds good, it looks good. I think it's an improvement over what's on the left, but it's not based in any physics. There's nothing in conduction heat transfer that says that this should be a linear relationship between inverse time to ignition and Q. It's just that it gives a number that I think is more accurate. So you want to be careful because it is an extrapolation. You can see you're extrapolating on that plot on the right beyond where you have the data. And not only that, but you're extrapolating to infinite time. So those 2 things make me a little bit uneasy about it, but I still think it's better than what's recommended by the standard. So if you get, say, as in this case, maybe 6 or 7 ignition delay times, it's 6 or 7 different heat fluxes. You plot it this way, and from the x-intercept, you get the minimum heat flux for ignition. Again, a material that ignites at a low minimum heat flux has a high fire hazard. Okay, the next thing that you can plot is the ignition time versus the inverse square root of the heat flux. And again, you get pretty straight line behavior. And from the slope of this plot, what you find is called the TRP, thermal response parameter. And unfortunately, in this hour's material, there are a lot of variables that have kind of unusual names that I find not very helpful. Everything's a thermal response parameter. Thermal conductivity, specific heat. It doesn't really tell me much, but this is the choice of the nomenclature in the standard now. So if you plot your same data this way now, it's the third way actually of plotting ignition delay time versus external heat flux, then the slope of this is the thermal response parameter. And basically, and by the way, this square dependence, I'll talk about it a little bit later near the end of this hour, does have a basis in conduction in solids. So the slope here doesn't tell you anything about the minimum heat flux for ignition, but it does tell you that if you increase your heat flux, how much you'll also increase your ignition delay time. It tells you the relationship between the delay time and the heat flux. If you go all the way to the right, this is very long ignition times, and eventually with that vertical dashed line, the heat flux is too low and you never get any ignition. Okay, a material with a low TRP is more hazardous, just like a material with a low minimum heat flux for ignition is hazardous. So here are a couple of examples of ignition test plots that we did for densified wood. You would expect that if you take wood that's double or 3 times as dense, you can compress this wood and change the chemical makeup to make it more dense. It starts to burn less rapidly than regular wood. And we saw that behavior here. These are some real tests where what's shown here is the ignition delay time versus the external heat flux. And on the right-hand side, the thermal response parameter, the TRP. So in both cases, the densified wood, the red wood, has a longer ignition delay time than the natural wood. And so by making wood more dense, as you would expect, you have less flammable wood. Oh, I'm sorry, there's a hand up, yes.
When did you consider that in materials, for example, like materials that are really low in volatiles, like char, it's not, you don't have a flame that you can easily recognize that it has ignited. When do you consider that ignition has happened?
Okay, so the question is, how do you know when you have ignition? And at least for the tests that I've seen, which is standard materials like hardboard or wood, you first see a little bit of smoke, and then you may see a little bit of smoldering, like red smoldering. But when the flame first comes, it's a very dramatic appearance of a flame, and you can't miss it. So I think it's a good question for some other materials, some more exotic materials, where you may start to see maybe like a halo, like a little bit of a blue flame. And then in that case, I think there would be more of a judgment call. You'd have to look at it more carefully. But usually for the stuff, in all the cases that I've seen, it's not like that. It's kind of like a fire point test. Once it ignites, you get a big yellow flame that you can't miss. I hope that answers your question. Have you seen this, or are you thinking of a specific fuel that might do that?
I was thinking about biochar or charcoal. Like you rarely see a flame. You see like some smoldering in the surface, and slowly it's like a shrinking core. You get like an ash layer, and at some point it consumes. I think
Very good. Okay. Yeah. So if you put charcoal in a cone calorimeter, you probably would need to go to a pretty high heat flux, 50 kilowatts per meter squared. And as you say, you won't have a big gas phase flame. It'll start smoldering, just like your barbecue does when you're cooking outside. And in that case, I think the cone calorimeter wouldn't be a good test for ignition. You could use it for the burning test. You can measure the heat of combustion, but it will not be good for ignition test. But that's a great question. Thanks. But, it gets to the point that I made yesterday that a great way to protect against burning, protect against flaming, is to have a char layer. And now the chemical industry has really been discouraged and banned from most countries from adding flame retardants to clothing and home furnishings. And the number one way of preventing burning now is to increase the charring like this.
chemical engineering department, and there's a group working on coatings, and they're called mason coatings. So basically, it's kind of like paint that when there's a fire, it kind of expands, and it's a really porous material to protect the structure of like a building, a bridge, or something like that. It gives people time to exit the building until it collapses.
Very good. Yes. So if anyone didn't hear it, the question was about intumescent paints. And these are paints that look like regular paint. I'm sure many of the steel beams in these buildings have them, that when it gets hot, when that steel gets hot, the paint puffs up, fluffs up, and prevents heat conduction and protects your materials. And certainly, intumescent paints get tested all the time in the cone calorimeter. It's a very good use of it. Well, thank you. Yes?
Is that how they make fire doors?
What's that?
Is that how they make fire doors, the doors that have to be used in buildings that can catch fire, or it doesn't have to? It's more to spread.
Sure. Okay, so fire doors are required to contain a fire for a certain number of minutes and not allow it to propagate. And it's especially important for egress, like in a stairwell. And so you get rated fire doors for a known fire size. They're known that they won't fail until that time. So does that help answer your question? So usually the fire, these doors have some wood panel on them, but I'm sure they have a fire rating. But most doors, you want to make them out of metal, something that's not flammable. And in that case, you probably wouldn't test them in the cone calorimeter. But perhaps these doors were tested there. Thank you. So the second parameter that you can measure with the cone calorimeter in its ignition testing mode is the minimum temperature for that fuel to ignite. So I spoke before about the minimum heat flux for it to ignite. And you can also measure the minimum temperature. Of course, a safe fuel has to be at a very high temperature before it ignites. And this is in the nomenclature called T-ignition, the ignition temperature. It's kind of like the fire point for a liquid, except that now it's ignition temperature for a wood. It's harder to measure. It really depends if you ignite it quickly or you ignite it slowly, because the species coming off depend on how much time it's been heated. But it's a sort of a pseudo measure where you have to accept some level of uncertainty in the value that you'd measure. So in some cone tests, people will actually just put a thermocouple in the surface of the material and measure its temperature. That really would be the ideal way to do it. But it's always difficult to put a thermocouple. Again, you have trouble with thermal contact. It may damage the material. And so there's a simple scaling analysis that you can do, a heat balance, that's shown here. So it's a heat balance now between the heat coming in and the heat going out at a quasi-steady condition. At the minimum heat flux, usually, it takes 5 or 10 minutes for it to ignite. So you can consider that it's, after 5 minutes, a quasi-steady condition. It's not changing very fast. And if we do this heat balance, shown in the sketch at the right, the incident heat is just the heat flux from the radiant panel. That's the Q min, maybe about 15 kilowatts per meter squared. And then that panel is not really conducting heat anymore because it's had 5 or 10 minutes to get up the temperature. There's no conduction into the depth, but it's losing heat by radiation and by convection. So we can do this heat balance then. There are the three terms as shown in the first equation here. The minimum heat flux is the heat coming in, and you have convection going out, H delta T, and radiation leaving, epsilon sigma times T to the fourth. So this is the kind of very simple heat balance that you often use for burning solids. The convection coefficient for turbulent flow, natural convection over a flat plate is about 15 watts per meter squared Kelvin. The Stefan-Boltzmann constant is shown next. Almost all fuels behave with an emissivity pretty close to 1. I showed yesterday that for smoldering embers, because of ash, emissivity times the transmittance is more like 0.8. But here, just to get in the ballpark, we'll call it 1. And the ambient temperature is 300 kelvins. So usually you can't solve this analytically, but you know everything in this equation except T ignition, the ignition temperature. You know the minimum heat flux that was required for the ignition because you performed those 7 tests. And so on the right-hand side, you have basically T ignition as your only unknown. And you can solve this equation just by making this kind of very approximate type of heat balance. So what this means is that after you do a cone ignition test and you measure the minimum heat flux for ignition, with a simple balance like this, you've also measured the minimum temperature for ignition. Okay, so let me back up this. So this is the end of the cone ignition tests, where the main parameters that we've been able to measure are the minimum heat flux for that fuel to ignite, the minimum temperature for it to ignite, and the TRP, thermal response parameter, which kind of tells you, as you change the heat flux, how much do you change the time, the delay for ignition. And with that, I'll make a transition here to the, oh, yes, question?
Yes, so it's about the heat flux to ignition. So you mentioned in the beginning that there might be some quality changes. For example, if you have PMA, it might slightly wash. So then you get closer also to the film, so you'll have more heat flux in that thing. right, compared to the original agreement
Yes.
that you had. So how does that then change the test that you're doing?
Okay, so that's an excellent question. So the question is, if you're doing PMMA, and PMMA, polymethyl methacrylate, is very attractive for a cone because it's basically a monomer. It's a polymer that boils and only one molecule comes off, which is MMA. So it seems very attractive. It's used very widely in fire studies. But as you said, it can bubble and boil, and it can expand and puff up. And there are lots of fuels that do that when you put them in the cone calorimeter. And in some cases, it'll expand so far up that it actually starts to touch your heater coils. And this is a real problem. So usually what you do in that case is you'll take a metal mesh, like chicken wire or some kind of a wire mesh, and put it on top of the fuel to maintain it in its condition. So usually when I do this for teaching, we use something that's really well behaved, like plywood or hardboard that doesn't do those. But if you're testing an intumescent paint, of course it gets up closer to the radiant panel and has now a higher heat flux. And you have to account that for that in the tests. In some, you can lower down the specimen, so you can manually move it away. But that's just one of the issues that's very complicated in burning solids.
If you have that something that bulges instead of laying on.
Sure, if it starts bulging, you have more surface area, you're absorbing more heat, more surface area to evaporate. If it's bubbling or, cracking, you have more surface area. So all those things change the burning behavior. And, one of the best ways to account for that is just to do a lot of repeat tests to account for that complication. And so, all the combustion people in the room, you're lucky. You don't have to worry about bubbling and cracking and deforming and unknown burning rates. It's, I know everyone's got working with hard problems, but the fire problems are very specific to fire research. Okay, so let me change gears a little bit. This is still the cone calorimeter, but now at the instant that that fuel ignites, you transition. You're no longer doing an ignition test where you're learning about the minimum heat flux for ignition, and you're doing the cone burning test. And it's equally valuable. It's very nice out of one standard to be able to get two different tests. But now I'm transitioning, and we'll talk about the cone burning tests. And so I want to draw your attention to the sketch at the bottom. Again, there's the specimen 10 by 10 centimeters and a heater with an external heat flux Q irradiating your specimen. So that's the cone. This is why it's called the cone calorimeter, because it's a conical heater, and it's open so that all the products of combustion enter into the cone. And it's a calorimeter. Okay, this is the cone calorimeter test. It's the really most valuable of all the fire standard tests. And the calorimeter is because you're measuring the heat release rate. Okay, so in the burning test now, we're going to measure these four critical components, characteristics. The burning rate, basically that's dm dt, d mass dt, and we measure that by having a load cell under the specimen, and you constantly measure the weight, and from that you can get the burning rate. It's a little tricky because it's a turbulent region, and you get a noisy signal from the turbulence. Sometimes you have popping, or even wood will break off and fall off. And so sometimes it's a little bit difficult even to measure the mass of your fuel. The second one here on the list is the oxygen consumption rate, M.O2. And this is really a key aspect of the cone calorimeter that really I think is the reason that it's such a famous and such widely used standard, is that it measures the oxygen consumption rate. It does its calorimetry. It measures the rate of heat production in a burning, not from measuring the heat, but really the opposite of that, measuring how much oxygen is consumed. Okay, it measures then the heat release rate, and finally the heat of combustion. And the heat of combustion is the main fuel property that you can measure with the cone calorimeter. And of course, something with a high heat of combustion, like methane, all the hydrocarbons, methane, ethane, propane, have high heats of combustion. Of course, per gram, they liberate more heat, and they're more hazardous than something with a lower heat of combustion like wood. So this is a schematic of the exhaust duct and what that looks like in the cone calorimeter. So you start with the load cell at the right, supporting the fuel specimen. Just above that, you have electric heater, the heater that stays on throughout the entire test, not just for the ignition. It's usually open to air at the bottom, but with windows so that you can look in. And so with those arrows, then you can see the streamlines of the air, some of the air going through the cone and some coming around it, about 10 times as much air as is needed for stoichiometry. And then the flow makes a left-hand turn and passes through an orifice plate, that thing that looks like a blue donut. And so that first orifice plate promotes mixing, makes sure that your sample gets all mixed up really nicely. And once it's mixed, then there's a gas sampling ring probe. So you pull out a gas sample and measure the oxygen concentration. And it's actually from the oxygen decrement, the decrement in oxygen concentration, that you back out the heat release rate. And then it goes into the blower. It's a big, loud motor that blows a lot of air. And downstream of the blower, then, you measure the temperature at the exit. You measure the pressure, that P1. And then there's a second orifice there, another orifice plate with the same diameter that creates a pressure drop, and then you measure the second pressure. So downstream of the blower, you measure two pressures, so you measure a pressure drop and a temperature, and that's how you actually measure the flow rate. So in order to do the calorimetry, you need to know the flow rate. That's going to be measured with those two pressure transducers. And you need to know the oxygen concentration, which is measured with the gas sampling. And I think all this together is the beauty of the design of this instrument. The beauty that it can do ignition tests and burning tests, that all the fuel products are captured in the hood, and the clever way in which it measures, without an expensive flow measuring system, the flow rate and also the oxygen concentration. So in a nutshell, this picture kind of shows to me what's really beautiful about the cone calorimeter and the reason it's such a widely used fire standard. So let's talk a little bit about the orifice flow meter. So you can buy flow meters that are measured these, I guess it's a 6-inch duct. They can measure flows like this, but they're expensive. And you're not just measuring the flow of air, you're measuring high temperature air, so it has to be temperature corrected. And then you've got a lot of soot and maybe acids, things that will damage that flow meter. You can't really measure the flow very well upstream. You have to measure the downstream flow. So it's a beautiful design that just by using an orifice and two pressure transducers, you can actually measure the flow rate. And so what's done here, as I mentioned, is you measure P1 at all times, P2 at all times, and the temperature with the thermocouple, and plug that into a simple little Excel spreadsheet is what we use, and you know the mass flow rate as a function of time. So this really comes down to the Bernoulli equation. You look at it, do a Bernoulli balance between P1 and P2, and that's given here by that first equation, P1 plus 1/2 rho V squared equals P2 plus 1/2 rho V3 squared. Remember in the Bernoulli equation, and this is going back to sophomore, junior year, all the velocity at station 3 gets mixed out through turbulence, and you don't recover that velocity. So it's not, on the right-hand side, P2 plus 1/2 rho V2 squared. It's 1/2 rho V3 squared. And so we can do a little bit of algebra around this and come out with an expression just based on Bernoulli that relates the pressure change, the delta P, back to the mass flow rate. And that really is the last equation here. It says that the mass flow rate is proportional to square root of pressure divided by square root of temperature. So if you measure that pressure drop, take its square root, divide by the square root of the temperature, then that's proportional to the flow rate. And this C coefficient here, actually, you can back that out of Bernoulli, you can do the math, but in the end, it's pretty approximate. And so instead what we do is we actually measure that C with a methane flame. We burn a methane flame in the burner, and we know exactly what the heat release rate is. We know exactly how much methane is flowing, how much heat's released, and we calibrate the flow rate, this flow meter from that measurement. So Bernoulli kind of gives us a scaling, but the calibration doesn't depend only on Bernoulli. It's actually measured. Okay, so the next thing with the cone calorimeter is, you need to measure the flow rate out the exhaust, you need to measure the burning rate of the solid, and then you need to measure the oxygen concentration. So oxygen concentration is measured with this ring probe at that sketch on the right. It's a ring because even though you have an orifice plate and it's turbulent, it should be well mixed, you still want to sample from 20 or so different points circumferentially around to make sure you get a good representative sample. And then you pass this into an oxygen sensor. Now, there's a lot of math that I'm not going to show here because the oxygen sensor can be damaged if water vapor gets into it. It can be corrupted if carbon dioxide gas gets into it. So first, you scrub both of those out, and then you need to account for the amount that's been scrubbed. You measure the oxygen concentration in your analyzer, but to back that out to the oxygen concentration in the exhaust is a lengthy set of algebra that needs to be done. The good thing is that these paramagnetic analyzers, they last forever. Ours is 50 years old, and they give you 4 digits of accuracy. So when you turn it on and you're running air and it says, 0.2107, you can believe probably at least 3 of those digits. It's a very accurate way of measuring oxygen concentrations. It's an expensive device, but a very accurate device. So then if you measure the flow rate, m dot E, the mass flow rate out your duct from the pressure transducer, then the oxygen consumption rate is just the difference between the inflow rate of oxygen, which all comes from the air that's flowing in, and the outflow rate of oxygen, which you measure with your oxygen sensor and the flow rate. So basically, this is how the calorimeter works. There's a control volume analysis with the dashed line that's shown there. And from this analysis, then, the flow in, the rate of flow of oxygen in versus the rate of the flow of oxygen out, you measure the oxygen consumption rate. That's the m.O2. And that's how we do our calorimetry. There are other ways, there are other standards where they actually measure the temperatures, but it's never as accurate. You try to measure the temperature in the duct, and the duct is hot. The big signs on ours say, do not touch. It's not red hot, but you'll get a burn. So by measuring with thermocouples, you never get a very satisfactory measure of calorimetry. Now, this is the fundamental premise of the cone calorimeter. How do you, once you measure the oxygen consumption rate, how do you convert that to a heat release rate? And this, again, is one of the great successes of this standard. And the way that you do the conversion is that it's a direct proportionality. If you multiply the oxygen consumption rate by this magic number, 13.1, it will give you the heat release rate. And it will give you the heat release rate for almost any fuel. Now, the other way you could do this is you could measure the fuel burning rate. We have a load cell. We know how many grams per second of fuel are being burned. And if you knew the heat of the combustion of the fuel, you could multiply that. But usually in the cone calorimeter, someone's giving you a piece of carpet, piece of wood paneling, maybe a piece of fabric or a piece of wood, and you don't know the heat of combustion. And the beautiful thing about the cone is that all fuels have a heat of combustion per gram of oxygen consumed of about 13.1. So the lower heating values, as I show at the bottom, vary all over the map. For methane, it's 50 kilojoules per gram. For hydrogen, 120. For wood, it's somewhere around 20, depending on the wood. So if you're doing the standard combustion, lower heating value, heat of combustion times the fuel burning rate, every calculation is going to be different. Every fuel has a different heat of combustion. However, in terms of oxygen consumption rate, all these fuels have the same heat of combustion per gram of oxygen consumed, which is 13.1. So whether you're burning methane in the cone, you're burning wood or carpet, whatever you're burning, if you can measure the oxygen consumption rate, that's the m.O2, which you measure with the pressure gauges and the oxygen sensor, and you multiply that by 13.1, that gives you a heat release rate. So it's the fundamental premise of the cone, and maybe some fuels are not 13.1, they're 14 or 12. You have to accept some uncertainties when you do fire studies, but this isn't one of the biggest biggest uncertainties in the cone calorimeter. It's, to me, one of the great successes. Okay, so remember now that the load cell measures your fuel consumption rate as a function of time, and it's not usually constant. It's not like it ignites and the fuel consumption rate stays at a constant value and then falls off. You're burning complicated things like wood. It's cracking and popping, and the m dot of fuel, it's noisy. It's bouncing up and down, going all over the place. But, and as is the heat release rate, the HRR. But if you take their ratio at all times, heat release rate and the m dot of the fuel, and you divide those two, then you find from this the heat of the combustion. You want to average it over the whole 30 seconds or 1 minute of the burn, but you can now, with the cone calorimeter, measure the heat of combustion. You know, the other way you might do this heat of combustion is with the bomb calorimeter. It's the same way they measure the calorie value of foods. If you're selling cereal, you take this stainless steel vial, you put a few grams of your cereal in it, you fill it up with pure oxygen at 30 bars, okay, so very high pressure, and you burn all of it. You spark it, you make sure everything burns, and it's in a water bath. And you measure the temperature of the water. And so when you buy foods, this is how their basically heat of combustion, their calorific value is measured. But that's not a very satisfying way for fuels. There's a lot of inaccuracy in that, and you don't get to see what's burning. It's much better to measure heat of combustion for fires, for condensed fuels, using a cone calorimeter. Okay, so here's an example of a heat release rate plot, and this shows the heat release rate versus time of the same fuels I showed before, natural wood and densified wood. And in this case, you can see that the natural wood, regular untreated wood, has a really high peak heat release rate and burns out faster, but the densified wood burns with less heat release rate. Okay, with that, I'm going to change gears a little bit and now talk about the lift. This is the lateral ignition and flame spread test. It's I won't spend as much time on it because it's not nearly as impressive as the cone calorimeter, but it does have some interesting analysis that goes with it. We also have a lift in our department, and all our undergraduates also do a test with the lift test. Okay, so this is lateral ignition and flame spread test. There are about 20 of these in the world, so they're not nearly as popular. And it also, like the cone, has two tests. It has an ignition test and a burning test. And it measures some of the similar things, the minimum heat flux for ignition, the temperature of ignition, and the thermal response parameter. So it's shown here on the right. It's about, again, as big as this podium plus one of the side tables, so it's a rather big apparatus. And I'll show you some more details in a minute. So at the lower right, you can see a lift test that's burning. Basically, the specimen is vertical, and so this is a view from a camera on the floor looking up at the fire. And the specimen ignites on the left, and as it burns to the right. And you track always the leading edge of this flame with the video camera, and eventually the flame will go out. The reason it goes out is that there's a big radiant panel. You can see that better on the image at the left, and this radiant panel then is providing an external heat source. Because it's oriented at an angle of 15 degrees, the left side of the specimen, which typically, in this case, it looks like plywood, the left side of the specimen has a higher external heat flux and burns quite quickly. And as you move far enough to the right, you have almost no external heat flux. And for this reason, most fuels will not burn all the way to the end of the specimen. Okay. So the size of the specimen is 0.8 meters long by 155 millimeters high. You run it first with a square specimen all the way at the left side to do your ignition test. And once you've completed the ignition test, you use a full-size specimen, this rectangular specimen, and watch the flame spread. And again, it's an ignition test on a vertical specimen and a flame spread test. If you're characterizing the burning of solids, You want to know about the ignition properties. You want to know about the burning properties, and we get 2 of those for a horizontal specimen in the cone. And then you want to know about the flame spread properties as well. Safe solid fuels, hard to ignite. They don't burn with a lot of heat, and they don't spread very easily. So just like the cone, the lift is split up into 2 parts. Part 1 is ignition, and part 2 is spread. And the ignition test for the lift finds 5 key properties. Much like the cone, it finds the minimum heat flux for ignition. It finds something like the TRP from the cone, but for some reason it's now called B. Instead of thermal response parameter, it's ignition correlation parameter. Neither of those is the choice of words that I would use for them. And to have 2 things that represent the same thing also adds a little to the confusion. Just like the cone calorimeter, it can measure the ignition temperature, although now with a vertical surface instead of a horizontal fuel. And for the ignition, it can also estimate the equilibrium time, how long for the fuel to come up to temperature to ignite, and what's called the thermal inertia. Thermal inertia comes up a lot in solids burning. It's the thermal conductivity times the density times the specific heat. So all 3 of these will tend to keep a surface cool. If you have a radiant source on a surface of wood that has high thermal conductivity, it'll keep the surface cool. If it has high density, it keeps the surface cool. And or if it has high specific heat, the surface stays cool. Fuel surfaces that stay cool under radiant heating are relatively safe. If there's a fire on one wall in a room and you have a radiant heat far away, you want a surface that has a high K times rho times C sub P, because that surface will stay cool and hopefully below its ignition temperature. So there are 2 key assumptions for the lift ignition test. First, that the fuel is thermally thick. And second, like the cone, that you have a fire point for the solid. If that surface gets to the ignition temperature, T ignition, then when there's a pilot present, as there is in the lift here, it's actually an acetylene flame, it will ignite. So based on this, we can do a simple 1D transient heat transfer equation. Thermal thickness is really important for fire studies, whether a fuel is thermally thin, like a sheet of paper burning on the right, or thermally thick, like a piece of plywood burning. And the basic difference is that if you're thermally thin, then the temperature is constant across that sheet of paper. The paper is thin, so you have constant temperature. If you're thermally thick, it's the other extreme limit. The heat that's applied to the left side of the fuel never propagates to the right side. So, the backside of this fuel always stays at the ambient temperature T infinity. Those are the 2 limits. It certainly depends how long the flame is present, but while the flame is present, if you're in either of these limits, thermally thin limit or thermally thick limit, then the math is relatively easy. If you're in between, which actually happens with lots of flames that persist for a long enough time, you're neither thick nor thin, and the math isn't near, the analytical solutions just don't exist, then you need to go to a computer model. So we can do the same kind of surface heat balance with the lift ignition test as I discussed before for the cone calorimeter ignition test. And so what happens here is if you plot distance z on the x-axis versus the temperature, as soon as you impose the heat flux, the temperature of the surface starts to increase, and it increases until that surface temperature gets to the ignition temperature. And what I want to point out isn't that clear in this sketch, but when you get to the ignition temperature, that slope at the surface, d temperature dz, actually decreases. So I'm running a little bit short on time. I think I will skip through a few of these slides. They'll all be in the PDFs that we finally post, but I'm going to skip forward a little bit. This is the surface heat balance, and the ignition temperature, very similar to how ignition temperature was calculated for the cone, but often it's a little bit different when you have a vertical specimen compared to a horizontal specimen. So for this ignition test on the lift, lateral ignition flame spread test, we can solve the heat equation. So we're interested in the conduction heat transfer. And this we all know from our junior year heat transfer class, d temperature dt equals thermal diffusivity times the Laplacian of the temperature. In 1D, this becomes this differential equation. It's a second order differential equation with the boundary conditions as shown here. Now, that's a hard equation to solve, but it's been solved under reasonable boundary conditions, and we'll do that next. And I'm kind of speeding up here. It's solved with a similarity solution, kind of like a boundary layer over a flat plate. Here, you get a similarity solution for the heat transfer in the solid, and it's expressed in terms of the error function. Bejan has this beautifully laid out in a textbook. You'll have now tau is a dimensionless time, error function appears here. And finally, at the last equation, you can relate the time, so how long this fuel specimen has been irradiated by, say, 20 kilowatts per meter squared, that's your tau. And on the left-hand side is the left-hand side is your heat flux, expressed in terms of the minimum heat flux divided by the actual heat flux. And on the right-hand side is how long until that surface becomes flammable. Okay, so this is a relationship between the actual heat flux and the time to ignition. So there's some approximations that are made here that are shown in the first line, and then a new parameter that's introduced. But in the end, what you find here is the main equation, Q min over Q is equal to B square root of T. What it says is that for a given heat flux, that this scales with the square root of ignition delay time. Higher heat flux, it ignites in a shorter time. And that solution is actually used for the cone calorimeter, as I showed earlier. Okay, so if you plot the same data, it's very similar to how the cone is plotted. Square root of T ignition on the x-axis, Q over Q on the y-axis. As you go to higher heat fluxes, you're working your way to the left, back toward the origin. And if you go to low enough heat fluxes, eventually you get to those two dashed lines where nothing will ignite. But this is really similar to the plot for the cone calorimeter, except that for some reason they use TRP for the cone calorimeter, and this characteristic is called B for the lift tests. Okay, now that I've covered in a very cursory manner the ignition test for lift, let's talk about the spread tests for lift. So the flame spread test looks like this. You have the heat flux Q, and it's oriented at 15 degrees to your specimen, kind of as drawn to scale here. The left side of the specimen will always ignite and burn, and as the flame moves to the right, it gets farther and farther away from the heat source until actually it usually extinguishes. And the point where it extinguishes is an important measurement of the flame spread. So the flame spread test can measure the minimum temperature of the fuel for the flame to spread. It can measure the minimum heat flux at that location for the flame to spread, and also the spread velocity as a function of T. Of course, you know, for a safe fuel, you want a fuel that has a very slow rate of flame spread. And this is what we can measure with the lift test. All right, there are lots of different kinds of flame spread. Flame spread can be thermally thick or thin. Flame spread over paper is usually thin. Flame spread over wood is usually thick. And the lift analysis assumes that it's a thick fuel. It can be vertical spread, like spread up curtains or a wall, which usually is a very high rate of spread, as you see with facade fires. Or it can be horizontal spread. The lift test is a horizontal spread test. And flame spread additionally can be concurrent with the wind, opposed to the wind, or lateral to the wind. So people who do flame spread, usually they'll emphasize one or two of these configurations because each one has a different set of equations and assumptions and analysis and different kinds of tests. So maybe one of the easiest flame spreads to consider is a circular flame spread. For example, arsonists sometimes will pour accelerant on carpet and ignite it. And in this case, you start with a small flame that propagates out, kind of like pools on ripples on a pond. And you get then these concentric circles of the flame spreading. It's an outward flame spread. And it turns out that, of course, if it's a constant rate of spread, then the area increases with the square of time, or as shown in the bottom plot, the heat release rate scales with time squared. And this is one of the most famous design fires in fire protection engineering. It's called a T-squared fire. For most fire designs, you have a design fire is usually a T-squared fire. It starts small, and then the heat release rate grows parabolically. So this sort of a round expanding out fire is the basis for the T-squared fire. It turns out, though, even if you have a trash can fire, the heat release rate tends to scale with T-squared. So in the lift spread test, it looks like this from the side. You have char on the left, which really, as I mentioned, has a vaporization temperature of 4,000 kelvins. It's hard for any flame to burn char in the gas phase. Of course, once it starts burning in the solid phase, it's a different story. It's smoldering. And then on the right, you have the virgin fuel with the flame that dances around and has a shape kind of like this and spreads to the right. So from the bottom view of the spread, in terms of the fire analysis, we consider the virgin fuel off to the right at 25 degrees C, and then a region called P, which is the preheat region under the flame. This is a region that's heated mostly by the flame, but also a little bit by the external source. And then that area called pyrrole, it's the pyrolyzing region. This is the region that's actually liberating a lot of the gases that drive the gas flame. And then behind that, to the left, behind the flame, is the B, the burned out region, that often will be smoldering, but cannot support a gas phase flame. So there's a nice little theory of the lift flame spread, and it's predicated on this plot at the right that shows the heat flux as a function of position for the specimen. So as I mentioned, as you go all the way to the end of the specimen at a distance of 800 millimeters, there's almost no heat flux from that radiant source. But at the upstream end, at the far left end, you have very high heat flux, often 30 or so kilowatts per meter squared. So we do a few heat balances that I don't have time to cover now, but the main thing we're going to do in one of these tests is to observe the flame, see that it ignites and it burns to the right, and it burns past the location of Q min. So the flame continues to heat the fuel so that it will burn beyond the point where it would be ignited. Remember, Q dot min, that horizontal line, is the minimum heat flux for ignition, but the flame keeps going all the way out to the location of Q minimum of spread. So in the spread test, that's an important parameter you want to be able to measure. What's the external heat flux required for a flame with its additional heat flux to continue to spread? Okay, so there's an expression for the velocity. This is, the derivation is not shown here, and I don't have time to even cover what I have on the slide, but Quintiri's text covers that for the spread velocity. And then simple expression for the surface temperature at each location at each time. And then in the end, this will be my last slide for this part of the day, you can plot the position versus time. So you get a video and you track the position versus time. Those are the plus marks. And as you move to the right, you can see that time increases faster than position. And if you do the derivative of this, you can plot velocity versus time on the left axis. So, velocity versus position. The initial fire moves very fast, spreads fast, and as it moves to the right, the surface is cooler, there's less external heat flux, and it slows down until it falls off the cliff and extinguishes. But most importantly, then you can convert that data to a plot of velocity of the spread versus temperature. And of course, you want safe fuels to have a low velocity of spread at a given temperature. And you can see from this relationship, for all the temperatures in this test, which aren't measured but are modeled, what the velocity is. And then, of course, the minimum temperature for spread. And I do believe that's my last slide. So let's reconvene in about 10 minutes at 4:30 for the last hour of the summer school.